All right, so we are getting into this last section. It's still about collisions, so that has not changed. But what has changed is now we're in 2 dimensions. So we have dealt with everything in 1 dimension in this unit already. That's why everything's been reviewed. But now we get into 2 dimensions. So in order to do this, we're going to need to do some vector addition. So when dealing with 2 dimensions, when we find total momentum, we have to do vector addition. So yes, not yesterday. Yesterday? What day is today? Today's Tuesday. On Sunday. On Sunday, when you did the momentum section, we talked about conservation of momentum. So momentum initial equals momentum final. And we're going to be doing the exact same thing today, except 2 dimensions. So the questions that you see will not be much different than what you've seen before, and the overall solution to the problem is similar. Just how we do the math is going to be different. So let's try this first one. We've got 2 cars. They're traveling in different directions. They're going to hit and they're going to stick together. And we want to know what's the final velocity. So let's draw out what's happening here. So I've got 2 cars. I've got a Hyundai and a Fiat. They're driving. One is moving west. One's moving south. So let's draw it like this. Here's our Fiat. Here's our Hyundai. When I was young and naive, I used to think Hyundai and Honda were the same thing. They just pronounced it differently. So here we go. We've got 2 objects that are coming towards each other. And in the final position, we're going to have these 2 cars. They're going to be squished together. And what direction approximately do you think they're going to go? If they're going like this, they're going to go someplace down this way. So this is what we're looking for. This is VF. We want to know what is this. That's a terrible question mark. There we go. So the key thing in doing this is knowing it's not velocity that is conserved, it's momentum that is conserved. And this is going to trip up a few people on a test. Remember, it's momentum conserved. So anytime I'm dealing with something in this question, I need to deal with momentum initial equals momentum final. So what I'll need to do first is find out, okay, what's my momentum 1 initial, or we can call this momentum F, since we're dealing with, no, that's going to get confusing. Let's just do 1. So we have momentum 1 initial, and we have momentum 2 initial, and here this is going to be momentum total final, because they're going to be stuck together.
Mr. Random, can you name them P, H, and PF?
I didn't want to because I'm going to have a final over here. So I didn't want a PFF. It doesn't really matter. If you wanted to label them as F and H, it really doesn't matter. So first, let's figure out what our momentums are. So this is simply going to be M1 V1I. Similar to what you've seen before. I've got the mass of the Fiat. It's over there. I've got its speed. So this is going to be 680 times 18. And plug that in the calculator. What did I get? 12,240. Anyone remember the unit for momentum? Newtons times seconds or kilogram meters per second. Either one's fine. It doesn't really matter. Find the second momentum. Again, you have the mass, you have the velocity. I'm not going to put the numbers in this time. And this. Newton seconds. Newtons times second. So there's our 2 initial momentums. Now in the past, we've simply done this. Don't write this out, please. We've done this in the past. So this is what we've done originally. And this works if it's in one dimension, because I can put this all in the same direction. I don't need to worry about angles. However, in this case, I do have angles. So this is going to be a problem. I cannot simply say that this plus this will give us the total. Instead, what I have is this. That my momentum 2 initial plus my momentum 1 initial, those two added up are going to give me my...
Add to take.
Yeah, I did. This is the resultant. So this is momentum total initial.
Does it matter if I do it now?
Yes, it matters. You mean this arrow?
Like it goes down, then what?
Oh, if you did down and then west, you get to the same point. Yeah, that way it didn't matter. I thought you meant the resultant. Doesn't matter what direction I do it. So, by adding these two up, I'm getting the total initial momentum.
Why not find?
Well, we're going to get there. So, what do we know about the conservation of momentum? The initial equals the final. So, the total initial is also equal to the momentum total final. So if we've solved for the total initial, we've solved for the total final. On your test, you don't need to show this, but I wanted to explicitly show you at this point so you could see what's going on with that. So these two are conveniently at 90 degrees. We're going to have some angle here. Now we can solve this. So momentum total final is going to equal the square root of momentum 1 initial plus momentum 2 initial, so just using Pythagoras, and we get total momentum, yes, sorry, that should be squared, yeah. So this should be 19. Okay, I got something slightly different. Could just be the rounding. So here's our total final momentum. But notice we're not asked for what's the total final momentum. We want what's the total final velocity. And note, velocity. Not speed, velocity. So that means I need both the magnitude and I need a direction. So I need two things. First, I need to take this, and this is going to equal mass total times velocity total final. I have the total final momentum. The mass total, I just add the two masses together. That one's not too bad. So then I get V total final is 14. So here's the magnitude. And to get direction, we're going to use tangent, so the inverse tan of opposite, momentum 1 initial, over adjacent. You could technically use sine or cosine if you wanted in the hypotenuse. Doesn't really matter. And this is 38 degrees. The question is, east of north, west of south. What is this?
West to south. No.
So look at what we're in reference to. We're right now in reference to west, and our resultant goes south of west. So this one would be south of west. If we set up our triangle like Khaled did, and we've got it down here, so let's just imagine we set up our triangle like this. If we solved for this angle here, what would that be? Now this one's west of south. My reference angle is south. The resultant goes west of south. So there's two answers you could have for your angle. Both of them would be correct. So here's our final answer. So 14 meters per second, 38 degrees west of south. Questions with this?
Are we always going to get them in right angle? No? Maybe.
Any other questions on this? So I'm taking two things that you've seen before and squishing them together. I'm taking conservation of momentum, you've seen it before, and combining that with all the vector addition we've done before. So you're starting to get to recognize, basically I am taking last year and adding a bunch of triangles. That is essentially what we do for a lot of this year. So remember, it is momentum that is conserved in this case. So we need to add the, I'm going to write it down like this, it's called momenta if it's just the plural of momentum, and it's not the velocities. So now let's get into non-90 degree triangles. So as per usual, we can deal with this in two methods. Component method, trig method. Again, sometimes there's going to be an easier one. You can pick whichever one you want. I think most of you are just like me and you would rather do component method. That tends to be the preferred method in everything whenever I've taught this. So let's first look at the question. So we've got a bowling ball. It's moving at an unknown velocity. It's moving east, so in no direction. And it's hitting a frozen cantaloupe. So after the collision, we've got the velocity and direction of the bowling ball and the velocity and direction of the cantaloupe. We want to know what's the initial velocity of the bowling ball. So lots of physics. We need to draw the diagrams. You don't have to. It just makes your life a whole lot easier if you can visualize what's going down. So that's why I typically draw this out. So we've got our bowling ball here. It's moving east. I don't know how to draw cantaloupe. Cantaloupe. There we go, it's a ball. So this is moving at some velocity. We don't know, let's call this mass 1, mass 2, and we'll say that velocity 1 initial, we do not know. That's what we're looking for. V2 initial is 0. So that's convenient. And then afterwards, these two things are moving in different directions. So what are we told? Bowling ball, 32 degrees north of east. So this one's moving like this, where this is 32, 2.8 meters per second. And the cantaloupe shrunk. There we go. This one is going 41 degrees south of east. So here's 41. And it's 1.5 meters per second. All right, any questions with the setup? Because if you can do this part, the rest of it is pretty straightforward if you can get this. If you mess up on the setting up the drawings, the rest of the question is going to be messed up. Yeah.
So after they collide, the velocity and the angle.
Yeah. So essentially, you've got this: two masses are coming together. They hit and go like this. So if you've ever played, if you've played billiards before, this is a classic question. Cue ball, 8 ball. They're just, yep. So it's a very common question, and this is you want to improve your billiards play. You can try and do these calculated in your head. So I'm just going to write down the masses here so I don't have to keep scrolling up. So here's our situation. Component method, you've seen this before. Break up your two vectors here to x and y components, add the x's, add the y's, draw a final triangle, everything you've seen before. So let's break these up. So we've got one that is 2.8 meters per second. Now, remember, it's not velocities being conserved, it's momentum. And here's where most students get tripped up with this, because with our two vectors here, we need to first turn them into momentum before we split them up. So that's typically where the biggest mistake comes in. So if we can still set up our triangle here, where this is 32. But before I convert this, I need to figure out what is momentum. Is this momentum 1? Yeah, momentum 1 final. So M1, V1, F. So we have the mass of the bowling ball. We've got the final velocity. So we can times those together. And I'm too lazy to try and do that in my head. 11.2. Just for the sake of being different, I'll use the other unit so you can see both. Please do not worry about any of your drawings being to scale in this. I'm never going to expect these to be to scale. So here it shows the x is much smaller than the y. If it is, it is. If it isn't, it isn't. I'm just caring about the numbers at this point.
So random, would you ever ask us to solve for a math?
Yep. I could ask you to solve for anything in this question.
We would have to solve like battery a lot.
This is why sometimes the trig method is easier. So if I was solving for mass in something like this, I would have a mass variable in all my different numbers. So these would both have mass 1 in it. Then when I combine the x's, there'd be a mass 1. So it's just a lot of algebra. But it is possible. I could give that to you.
Please don't.
You don't like algebra?
It's not that I don't like it. I tend to forget to write letters and numbers.
Oops. So then it would be great if you had a teacher who forced you to remember how to do that, right? Meters per second. And then break it up into the two components. So we've got momentum 1 final x is this, momentum 1 final times cos 32. Again, if you don't know where that comes from, it's just from SOHCAHTOA with a right angle triangle. I'm going to write out the equations first. And then write out some numbers. So we've got the y component, 5.935. X component, 9.498. In these middle parts, if you don't put the units like I'm doing here, that's okay. I'm not going to deduct you marks for that. If you want to be really picky about it, go for it, but I'm not going to be super stressed about that. 6.96. So in this, remember we're trying to figure out proper direction. So with our initial or final momentum, whatever we're breaking up, the direction matters. So I need to make sure that if there's anything in here that I need to put as negative, now's the time to do it. So any momentum that's to the right or up is positive. Anything that's left or down is negative. So this one needs to be negative. So don't forget to do something like this. You need to make sure if something's going down or if the portion is going down or if it's going to the left, you put it as negative. Any questions on this? So let's move on forward. So some of the X, some of the Y's, add them together. You have the numbers on the other page if you want to write them out. But we've got 16.404 kilogram meters per second as our X. And at our Y's, we've got negative 0.068. So with a number like this, we can say that this one is approximately 0. It's a very small number. And the reason why you can assume this, if you look at the other page, what are you told about the initial velocity of the bowling ball?
Still, no.
No, it's not. It's not still. What does it tell you? It's moving east. So if it's moving east, I should have no X component. Or sorry, no Y component, yeah. No Y component. So it shouldn't be having any up or down movement because it's purely going east. So total momentum is in the X direction. And there should be no surprise. So we're not done yet because we're asked to solve for what's the initial velocity, not what's the initial momentum. So we're looking for momentum initial in object 1, which is just going to be momentum, what are we doing? Is equal to momentum final. Momentum initial is equal to momentum final. It's purely the first object has momentum. It's going to equal the total final. And that total final is just purely what's here in the X direction. So I did a lot in that one statement, but I basically just said, here is my total final. That is equal to my total initial, which is just one object. Only one is moving, not both. So this is M1V1I equals our number here that we know. So this is equal to 16.404. So therefore V1I is equal to 4.1. And what's our direction in this case? Yeah, we'll get there.
Direction is east.
It's just east. You're already told it's east, but don't forget to write it.
Okay.
Yeah.
I have a question about the notice that momentum is all in the X direction.
Mm-hmm.
If it's not in the X direction,
If
do I
the
count for the 0.68?
yeah, so if it's not all in the X direction, what would we typically do once we've summed up X and Y's?
So how how did you guys do with reduced state if it's all in that direction? Some of it is
Due to some rounding errors with the numbers, it doesn't come out to exactly 0. So like I said, we can only assume it's 0 because we're told initially that it's purely in the east direction. If I did not tell you that, don't assume this is 0. Only if I tell you that. And Fady, to answer your question here with this, I'm essentially taking the fact that momentum initial is equal to momentum final. And my momentum initial is momentum initial 1 plus momentum initial 2. This is 0. And my total final, I just figured out, is purely in the x direction. There's no y direction. So that's how I ended up with the statement over there.
If we still solve for an angle or something with a different would it be wrong?
In this case, if you solve for an angle with this, yes. Purely because in the question I tell you that it's just east. So that's one way to go about it, is using component method. The other way is vector addition, which people tend to frown upon when they see it. But this one's actually a lot quicker. So notice that we're going to do this. We need our total momentum to be conserved. So momentum is conserved. So in order to do this, let's add these like vectors. So our momentum 1 final plus momentum 2 final, if I add those two together, we're going to get momentum total final, which we know is equal to momentum initial final. Or sorry, not momentum initial final, that makes no sense. Momentum total initial. So by adding our two final momentums together, we get the total final, because it's just adding them like vectors. And because of conservation of momentum, our initial equals the final. So we've got some angles in here. This is 32 degrees. We're told, let's move this out of the way. We're told up here is 41. So it should be pretty easy here to get this angle, since here's a Z roll. So therefore this has to be 41. If I know two of the three angles, the last one's easy. Just 180 minus those two.
negative 90.
Should be 107.
Okay. So calculate and what you That's right.
180 minus 32 minus 41. From here, it's pretty easy to get what the total initial is. So you could use cosine law and figure out the other side if you wanted to. You could use the sine law. Either one works. I personally prefer the sine law. It looks a lot nicer. So we could do momentum total initial over sine 107 is equal to, we could pick our whichever one you want, momentum 2 final or 32, or momentum 1, doesn't matter. Let's do momentum 1 final over sine 41. I have the number for momentum 1 final. I calculated on the previous page. So momentum total initial will give us 16.33. And again, We are not looking for momentum. We want the initial velocity. So just divide by mass 1. And I'm sure you are shocked that we get the exact same answer. And again, because we're told it's east, so we know the answer is east. So in this question, this one's definitely much easier and quicker.
Which side is sine?
Pardon me?
Which side is sine?
Here's 41. This is the opposite side.
Not equal to sine 107.
It's not equal to sine 107. I'm saying this divided by sine 107 is equal to this divided by sine 41. This is the sine law. What's that? Because it's the same question as before.
But you didn't know what you didn't use the
You're still told in the initial question that your total or your initial momentum is in the east direction. Otherwise, the angle would be big enough that you'd be able to solve for it. But in this case, you're told it. Which one? This one? That's this. Sine law. So this one you should know. All right, so that concludes the unit.